Hi there, this is my third video on an attempt to get something to move from one limit switch to another limit switch where it will delay and then go back to the original limit switch. So let's try it. If I press the button, hopefully the train's going to go across to this limit switch and then stop for a period of time and then go back to the start limit switch again. So there it is, it's going back again. The switches aren't very subtle, they're actually reed switches, which are just switches that have two contacts that come together when they're brought close to a magnet. So if we get a nut and bolt or something, we can see that there we have the magnet, and coming out, or at least in where these wires come from, inside there, don't know if we can see it, we have the reed switch. So how do reed switches work? Well, reed switches I've found to be a bit difficult, in as much as they are glass, which is good, because it means they can go down coal mines, for example, where if there's an explosion, then, or at least there's gas, then there won't be an explosion from a spark from the reed switch because it's enclosed. So here we have a reed switch, but fortunately it's broken. The glass is broken at the end and one of the reeds has come out. So it's RIP. I don't seem to have a great deal of luck with reed switches. But how do they work? Well, if we look at this one here, hopefully we can see, perhaps we need to zoom in a little bit. Are we there? Not quite. Doesn't want to focus on it. There we are, we've focused on it. Hopefully we can see the two reeds, one above the other. And if I bring a magnet close to it, so I bring a magnet closer, there, we can see how the reed switch operates and the magnet makes the contacts come together. On my particular setup, I've got the magnet permanently there, so the reeds are together normally, but when the train comes along, the reeds open up. So they're together, closed, and then they open up when the train comes along. I could, of course, alter my design and make it so that the reeds weren't quite as obvious, but that might take a bit more effort. And it's not what I particularly want to do. So that's the reed switches that I'm using. What about the 555 timer? Well, the 555 timer is a very old device, was around in the early 1970s, but it's still very useful and it has its applications. And this, I think, is one of them. So let's have a look at my diagram. There's my 555, everything inside the yellow box is what's inside the 555, and over here I have my relay. My relay then works as I've used before. We have a motor, the green lead comes down as it is here, comes up through the in switch, which is in the positive, and the blue comes down and is in the negative. At the moment, of course, the in switch is open, so the motor's stopped. If we energize the relay, we pass an electric current through the coil to make it magnetic, then the contacts move over. So what's happened is the green contact now has come to the 0 volts and the blue contact is now on positive. So that's when the train moves out. Once it gets out, it opens this switch here, and when this switch is opened, then the motor stops. So that's the function of the relay. But what about the 555? Well, this 555 has 3 resistors, each of 5 kilo ohms. Hence, some people say that's why it's a 555. If we have 9 volts across and each of these is the same size, then what we'll have is 3 volts here, and here 6 volts going into these gizmos. These then are called comparators. So if we look at a comparator, it has 2 inputs and 1 output. The inputs have rather long-winded names: the non-inverting input and the inverting input. The non-inverting is signified by a plus and the inverting by a minus. Rather confusing, but never mind. Anyway, the theory is that if the plus is greater than the minus, then the output goes high. If the minus is greater than the plus, then the output goes low. So that's our inverters here, but they're not much good because we want to remember. We want a sort of memory, a flip-flop some people call it, or a latch. So what happens is, with our latch, if the set goes high, the output goes high, and then when the reset goes high, the output goes low. And the output, of course, just goes straight to the relay. So how would we normally operate this? Well, under normal conditions, then what we have, just bring that down, what we'd have is a start. To set it, then we have a resistor pulling it high, so this minus is high, so therefore it's going to be higher than the 3 volts that are on the plus, so therefore the output's going to be low. But if I press the start button, then this minus will go less than 3 volts, it will go down to 0 volts, and therefore we will set this latch and the output will go high. On normal circumstances, there'd also be a connecting, a charging resistor and a capacitor. And what happens is, as soon as the start's pressed, then this capacitor will start to charge until it reaches above the voltage which is here, which in our case is 6 volts. And as soon as the capacitor charges above the 6 volts, then this output will be reset. How then do we manage to discharge the capacitor? Well, what we have then is a discharge transistor. So this transistor is low, as the discharge here goes low whenever the output here is low. So as soon as this goes low and discharges this capacitor. Whenever this goes high, then that goes off and is open circuit and does nothing. So as soon as the output goes high, this capacitor starts charging until this reaches greater than our 6 volts, when the reset occurs and the whole thing stops again. This is called monostable. But that ain't any good for what I want, because I don't want it to start discharging the capacitor charging as soon as I press the start. I want to wait until the train has hit the out switch. So how am I going to do that? Well, what I've done is to connect this green side of the motor, instead of it to the charging resistor, and instead of being connected to positive, it's connected to this green side of the motor. So as soon as this out opens, this is no longer at 0 volts. It's actually positive because it comes through the positive into the motor and out here into the green. So the green becomes positive. The charge resistor starts charging, and this carries on until the capacitor is above the, if this is 6 volts, it's greater than 6 volts when it resets. So that basically is how it works. Perhaps a graph would help, if we could have a look at a graph to see what's going on. So let's see if we can see that. So what we have here is our graph. The blue line then represents the pin 2, the start button. So here, when I press the start button, it goes down to 0, and when I let go, it goes back again. As soon as the start button, or pin 2, goes to 0, then the output, which is this red line here, goes high. So that's what's holding the relay on. So the relay's on all the time that this line is high. But what happens when the out switch is opened, then our capacitor starts to charge up. And it shows here, the green line is the capacitor charging until it reaches 6 volts. As soon as it reaches 6 volts, then the 555 resets and switches the relay off. At that time then, the train starts to go in the opposite direction as it is here, and so the train goes in the opposite direction until the in switch is opened there. I had some dilemmas with this as to what to do and how to discharge the capacitor. There is a pin 7 which is called the discharge, and that is what uses this transistor. So should I connect it or not? Well, if I didn't connect pin 7, what I found to happen was that the capacitor doesn't discharge. It goes along and it starts charging until it reaches its 6 volts, but then it carries on charging. And that's a problem, because if it hasn't completely discharged, and the only way it can discharge is through the charging resistor, so it's quite slow, so that then means that the timing is wrong. So I had to use the discharge resistor to be able to get it to operate reliably. So yeah, that's what I've done, and that's my 555 timer circuit. We can look at the diagram. Here's the printed circuit board diagram as viewed from the top. I flipped it so we can see it with the relay. So I have my out switch connects here, motor here and in here. Here I have my relay. Here I have my resistor for my power on LED. Here I have my 555. Here's the diode that goes across the relay to suppress the EMF, the back EMF, the voltage spikes, so it doesn't damage the 555. My start switch goes on here. I've used this variable resistor for setting the timing, and I've got my timing capacitor here next to a small capacitor that's used on pin 5, because we don't use pin 5. There's an on-off switch and a diode, so if it's connected the wrong way round, nothing happens, and my power comes in here. So yeah, I'm quite chuffed with that. I've enjoyed the journey. It's been a very long journey, but I seem to be there. If we set the train going, we can see the sort of current that we're using, 230 milliamps here, till it gets to the switch, when it goes down to 150 milliamps, which is presumably what the relay is taking, and then when it comes back, it's sort of using 60-70 milliamps until it gets to the end. I think those sort of currents should be perfectly acceptable for the reed relays, or the reed switches, sorry, they're not reed relays, they're just reed switches, and that should hopefully keep me going and keep me amused for quite a while. So it's bye now, bye.